I would like to continue on with the time that we have to introduce our next speaker. His name is Dr. Cameron Wobus. He is a principal at CK BlueShift, a natural resource consulting group affiliated with the law firm of Culp and Kelly. He has expertise in surface and groundwater hydrology, climate change, and numerical modeling. He is especially interested in projects that span the disciplines of science, economics, and policy. Cam lives in Boulder, Colorado, and collaborates regularly with colleagues at the University of Colorado. So thank Cameron for coming up today to give us a speak on his work. Here we are. Full screen.
All right, thanks. It's great to be here. It's a really super cool conference, and it's also been really good to see all these highly technical talks summarizing like comparisons and inner comparisons and all the super cool data. And I'm not going to do any of that. So in the spirit of this conference, having all kinds of different things going on, I'm going to kind of zoom way out, and look at how we can use OpenET data to quantify just big regional trends in water use for agriculture in the state of New Mexico. And this was funded by the Thornburg Foundation, so I want to thank Patrick McCarthy and the Thornburg Foundation for really being thought partners in this process, and then Caroline Nash at CK BlueShift and Mary Kelly at Culp and Kelly also. So, I should probably put it in slideshow mode. Oh, it doesn't change on my computer. Okay, so the objectives were to understand agricultural water use in New Mexico, pretty straightforward. We wanted to leverage OpenET data to document where ag water is being used, and develop simple and ideally replicable methods to evaluate spatial and temporal trends in water use. The second objective was to develop a tool that could really support planning and conservation. We wanted to provide data for local, regional, or state water planning efforts. We wanted to be able to quantify potential water savings from conservation programs, and we wanted to provide kind of foundational data to support grant applications, and I'll talk about that sort of towards the end. And because I work with attorneys, there's a disclaimer at the bottom. This is not intended to be used in any administrative or judicial water rights proceedings, so we'll just get that out on the table right from the beginning. This is really not going for me. I don't know what I'm doing.
Slide up here.
Okay, so just stick with the mouse. So our analytical approach was really, really straightforward. We're basically just doing an annual water balance at a 30-meter resolution across the state of New Mexico. We're compiling evapotranspiration from OpenET, precipitation from PRISM, and crop data from the cropland data layer. And many people have mentioned already that this is not a complete water balance. There's runoff, there's deep percolation. We're ignoring runoff and deep percolation. But what we're trying to do is take the incoming precipitation from PRISM, take the OpenET data from, or the evapotranspiration data from OpenET, and calculate like what is kind of a minimum irrigation requirement for each crop, for each pixel. And so to do that, we're using 3 key data sets. We're using the USDA cropland data layer, which a lot of people have talked about already today. Obviously, we're using the OpenET data. We're using PRISM as a proxy for annual precipitation. There are not any kind of perfectly gridded annual precipitation products out there, but PRISM is one good one. And then everything we're doing is annual. So we have all the data from 2016 through 2021, and we're doing everything on an annual basis so we can avoid any complications on when the irrigation season is, when the cuttings are, and things like that. And then all the analysis was done in Google Earth Engine and MATLAB. All right, now I know how to advance the slides. So the data inputs, I'm going to just quickly run through them. For a crop type, we use the USDA cropland data layer. Most people in this room might be familiar with it. It's a satellite and machine learning derived product at a 30-meter resolution. Basically just tells you which crops are being grown where across the United States. Zoomed in on the upper left-hand corner here, you can sort of see the detail that you get out of the cropland data layer. This is in the upper San Juan Basin, and you can see all those different irrigated crop circles with corn and wheat and alfalfa and so forth. Non-cultivated landscapes in the cropland data layer are directly from NLCD, so you also have shrublands and forests and things like that, and those are all shown on this map. Second data input, obviously, since we're all here, OpenET. We again use the ensemble average at a native 30-meter resolution, and we use the annual data. And again, zooming in on that upper San Juan Basin, you can see differences in the amount of total ET that's coming off of those irrigated crop circles. And so we're taking that into account in our analysis as we go, and I'll talk about how we did that. And then Prism, again, it's pretty coarsely gridded, but it's a gridded reanalysis product that estimates actual precipitation by month and by year statewide. And it's, again, relatively coarse, but we regridded it so it's the same resolution as all the other data sets. So all we did is, it's really pretty simple. We just adjusted the crop data layer, the OpenET data, and the Prism data, the same spatial reference frame. So we have stacks of data where we can drill down through all the data sets. We then found all the crops in New Mexico that have at least 5,000 acres in cultivation in each year. And that was really just a practical matter. We didn't want to deal with crops that are just tiny players in the state of New Mexico. So the data I'll show you in the following slides is kind of based on those data. We extract the annual precipitation and the annual ET from each pixel for each crop type. So at 5,000 acres per crop, there's roughly 20,000 pixels per crop at least. And then all we're doing is compiling the ET and then the net consumptive use. Again, we're ignoring infiltration and overland flow. But the net consumptive use we're assuming is just ET minus precipitation. So how much water at a minimum do you need to apply to each one of those pixels to get the ET that you're observing? And so this is what the raw data looks like for all the crops in New Mexico that have at least 5,000 acres in cultivation. On the y-axis, we're looking at the net consumptive use, again, a proxy for net consumptive use, evapotranspiration minus precipitation, or roughly how much irrigation do you need to apply to each one of those pixels. These are all box and whisker plots, so the blue box is the interquartile range, 25th, 75th, and median is the red line. And there, you can see there's quite a bit of spread across all these crops. Again, we're looking at every single pixel for every single crop. And so it's not unexpected, but when you start looking at the data, you can start coming up with some observations. First of all, pecans are a thirsty crop. And so you can see, on the order of 3/4 of a meter per year of applied water. Alfalfa, also a fairly thirsty crop, and quite a bit of spread in both of those. And that's, I'm not going to get into the details. There's lots more people here who know more about why there's spread in those data. But again, at a gross level, you can see there's quite a bit of irrigation required for alfalfa. And then crops that have corn in them, whether it's corn or popcorn or ornamental corn or double crops with corn. Corn is also a fairly thirsty crop. One of the things that was interesting coming out of this is that fields that are classified as fallow or idle cropland, the ET is not 0. And that's probably not surprising. There's still stuff growing on those fields, even if they're fallowed. And I'll talk about that a little bit more towards the end. So then zooming out again, we can look now at kind of the averages. We're going to kind of abandon all those box and whisker plots and just look at the mean, not the median, for each one of these crops over the 6 years that we analyzed. So for the rest of the talk, we'll just focus on these 7 crops: alfalfa, corn, pecans, winter wheat, other hay, sorghum, and cotton. And one of the things that was really interesting is year over year, there's not a whole lot of variability within a crop on the total ET. And so this is just straight up ET. This is not subtracting off precipitation. There's a little bit of variability year over year, but the differences between crops are a whole lot bigger than the differences within crops. If you start, now if you look at our proxy for irrigation required and you look at the ET minus precipitation for every crop, now you do start to see quite a bit of variability, and this is probably a climate signal, right? So in particular, Of the 6 years we analyzed, 2017 was the wettest. And so all those red bars that are from 2017 are generally smaller than all the other bars. You don't need as much irrigation when it's raining more. And 2020 was the driest growing season across the state based on the PRISM data. And so again, if you're not getting as much falling out of the sky and you have the same amount of ET from the previous slide, you need to apply more water to meet that irrigation requirement. So that we thought was kind of interesting. This has nothing to do with OpenET. This is just straight out of the cropland data layer. But there are some pretty clear trends in the state of New Mexico in cultivated acreage, at least based on what the cropland data layer is telling us. Alfalfa, a couple 100,000 acres, pretty stable. Cotton and pecans, 100,000 acres or less, also pretty stable. Big change in winter wheat and a big change in sorghum over those 6 years. And I don't know anything about crops, but I do know that sorghum prices were increasing over those 6 years. So it's entirely possible that farmers were like, hey, we can make more money planting sorghum, let's plant sorghum. So again, nothing to do with OpenET, but kind of a neat observation, I think. And then finally, the upshot of the whole analysis, if you just take the total acreage times the acre feet per acre, you can get an estimate of how much water is being used by each one of these crops across the state of New Mexico. Alfalfa, when you combine the total acreage with the amount of water you need, 400 to 500,000 acre feet per year over those 6 years. Pecans, even though they're a really thirsty crop, there's nowhere near as much acreage, so 100,000, maybe up to 200,000 acre feet per year. And then of course you can see the trend in sorghum, largely based on that, almost entirely based on that increase in cultivated acreage. And then we were contracted primarily to look at the Rio Grande and the Upper San Juan, and so that's why I was able to pull those irrigation districts out of this analysis. So we basically have EBID, San Juan, and the MRGCD, and then the rest of the state. And you can sort of see the breakdown of where those crops are being grown across the state and how much water is being used in all of those areas across the state. I think that's all I'll say about that. The other thing that we wanted to do, again, getting back to the original point, was to kind of evaluate conservation programs and be able to sort of get a handle on what kind of water savings you might expect from these sorts of conservation programs. And again, getting back to this idea of fallowed fields not always being created equal and not always having zero ET. If you look at the data, the fallowed fields clearly have lower ET than the surrounding fields. This little purple box here is one that was classified as fallowed by the cropland data layer. But the water consumption across that crop, across that field is variable, and it's rarely zero. And if you really zoom in and you squint your eyes, you can start seeing trends that might be related to proximity to irrigation canals that might be leaking, that are giving some available water to the plants that are growing on those fallowed fields. Clearly, there's a big difference when we looked at the Upper San Juan versus the irrigation districts along the Rio Grande. There's a whole lot more ET coming off of fallowed fields along the Rio Grande because there's probably a whole lot more available water in shallow groundwater and soil moisture right next to the river than there is sitting way up on that plateau up in the Upper San Juan. And so we thought that was interesting. And then we were able to get our hands on some shapefiles of fields that had been part of a fallowing program, and we could look at how much ET was coming off of those fields before they were fallowed and after they were fallowed. And so this histogram on the right here, the blue one is the net consumptive use, again, precipitation minus ET minus precipitation, before those fields were put in the fallowing program. And then the red histogram is the exact same fields after they were put in the fallowing program. And you can see that there is a shift of, roughly 300 millimeters per year of consumptive water use. And so this kind of analysis could conceivably facilitate the calculation of, what is the per acre water savings, what is the total water savings from fallowing programs. Which brings us to the next kind of phase of our research, was really to get a catalog of available grant programs And as we all probably know, there's this unprecedented array of grant dollars available out there right now, from the IRA drought mitigation funding, from water smart grants, and drought response programs. And so what we did is we built this table that just kind of summarizes what's the funding opportunity, where is it coming from, what types of things does this fund, and then how might you use OpenET data to be able to either apply for a grant program or to kind of document water savings through time. And so that was sort of, this is a table that was put into our final report. And really the idea is that if you have this kind of easy access to water use and savings data, that could really facilitate these sorts of grant applications, which we all want to see kind of accelerate water conservation in the Southwest. Okay, so just to summarize, the OpenET data for us supported a rapid assessment of agricultural water use in New Mexico, kind of documents where ag water is being used and which crops it's being used for. It illustrates, particularly in that analysis of year over year net ET, it illustrates the effect of climate variability on overall water use. And that could be really important for scenario development if you're looking at kind of future water use for the state of New Mexico. And then the idea is that kind of building this tool and making it available could support statewide water conservation efforts, could potentially inform state water planning, support grant applications, inform the design and implementation of agricultural water conservation programs, and ultimately, hopefully, quantify savings from projects once they're implemented on the ground. That's all I've got.
Thank you so much, Cameron.